Hello there, fellow math enthusiasts. Mrs. Delzati here. Today we're taking a look at UPS, Notes Day 4. We're going to be working with the probability of overlapping and disjoint events. So first of all, I want to do a quick review of what it means to be an intersection versus a union. When we're talking about an intersection, those are the outcomes that are shared by both of the events. So when we went ahead and we took a look at graphing inequalities, and let's say I plotted 2 points and I plotted an inequality that went this way and I plotted an inequality that went that way, the intersection of the two was what they went ahead and they had in common. When we talk about the union is all of the outcomes for either event. It's the combination of the two of them. For example, if we had something that looked like this and we had one inequality that went like this and another one that went and faced in the other direction, then the union of the two of them would be both of those put together. Now we also have a compound event, and the compound event is just what I just went ahead and I mentioned there. It's going to either be a union or it's going to be an intersection. When we talk about overlapping, it's when the outcomes have one or more outcomes that are in common. And we'll talk a little bit more about that as we do some of these examples. And then we have a disjoint or a mutually exclusive event. This is when the events have no outcomes in common. So when it comes to the probability of a compound event, we have A and B being any two events, and I want to talk about the probability of A and B. If we want the probability of A or B happening, we can go ahead and we can say the probability of A plus the probability of B, and then we're going to subtract off the probability of A and B. If we want to talk about the probability of A and B happening, we would take the probability of A, we would add to it the probability of B, and then we would subtract off the probability of A or B. Okay, I'm not going to lie, when it comes to A and B, it's a lot easier to count if you have a chart. Easier to count if you have a chart. All right, meaning if we're going ahead and we're talking about like a deck of cards, all right, and I give you the cards, it's either just to go ahead and say boop, 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 yep, those are the ones that I want. All right, so example, when I'm talking about this probability of A and probability of B, if for example, I said A was us being able to go ahead and to pull a 2, and B would be us pulling a heart. Okay, if I was talking about A and B, well, I would have 1, 2 of hearts. If I was talking about A or B, I would either have any of the 2s or any of the hearts. All right, now watch this thing. I think this is kind of cool here. This may look like it's a lot to go ahead and to memorize, but you don't actually have to memorize both of them, and I'm going to show you why. If we're talking about the probability of OR, and I say that that is equal to A plus B minus AND. All right, that's the first statement that I went ahead and I gave you. Now, if I go ahead and I want to get AND all by itself, I would have OR minus A minus B is equal to a negative AND. And if I went ahead and multiplied through everything by a -1 in order to clear that, well, that would give me a positive A, that would give me a positive B, that would give me a negative OR, and that would equal a positive AND. Take a look at the AND, that was A plus B minus OR. So if you can remember one of them, it's just a matter of going ahead and doing a little bit of algebra to figure out what the other one is going to be. When we talk about disjoint events, probability of A or B happening, well, we would have that this would just be the probability of A plus the probability of B. if it is disjoint, they don't have any of them in common, which is why this probability of A and B, that would equal 0, and you'd just be subtracting 0 off there. So let's go ahead, let's see how this works here. I've given us the deck of cards, and I'm telling you a card is randomly selected from a standard deck of cards. What is the probability that it is either a 10 or a face card? So if it is an or statement, I'm saying or is equal to A plus B minus and. So the probability of a 10 or a face is equal to the probability of a 10 plus the probability of a face minus the probability of a 10 and a face. So the probability of a 10, well, I have 1, 2, 3, 4 10s. That's 4 out of 52. The probability of a face, that is 3 times 4, that's going to give me 12 out of 52. And then the probability of it being a 10 and a face. Well, let's think about it. Could it be a 10 and a face? It can't be, okay? Since this is not possible, you can't have it be a 10 and a face at the same time. We're going to see here that this is a disjoint or a mutually exclusive event that is happening. So really all I have to deal with is the 4 over 52 and the 12 over 52. If I add that together, I have that is 16 over 52, which I can reduce to 4 over 13. And if I pop that in my calculator, that is approximately 0.308. Okay, so key thing that we need to remember here is this statement right there. The or is equal to A plus B minus and. Let's go ahead, let's flip it over and let's take a look at number 2. It said a card is randomly selected from a standard deck of cards. What is the probability that it is a face card or a space? Again, or is equal to A plus B minus and. So probability of a face card or a spade means we do the probability of the face plus the probability of a spade, and then we have to subtract off the probability of the face and the spade because we don't want to go ahead and double count those. So the probability of a face, that is 12 out of 52. The probability of a spade, well, that's 13 out of 52. And then face cards that are spades, there are 3 of those, the Jack, Queen, and King. So I have to subtract off 3 out of 52 because, again, we don't want to double count those. If I go ahead and I simplify that, that's going to give me 22 out of 52, which will reduce down to 11 over 26, which is approximately 0.423. All right, look at number 3. A card is randomly selected. What is the probability that it is less than 5 and it is a diamond? Probability that it is less than 5 and a diamond. Now, like I mentioned before, when it's the and ones and you're given a chart, it's a lot easier just to go ahead and count them. To be less than 5, you need a 2, a 3, and a 4. Keep in mind, ace is always high. And we want a diamond. So 2 of diamonds, 3 of diamonds, 4 of diamonds, we just counted them up. That is 3 out of 52 cards, which is 0.058. Okay, no need to actually go ahead and to write out the formula for that one. All right, look at number 4. Number 4 says a card is randomly selected from a standard deck. What is the probability that it is more than 3? So we want greater than 3. Let's go the other way, greater than 3. And we want it to be red. Well, if we go ahead, we take a look, we want it to be greater than 3 and we want it to be red. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times 2 of them, that will give me 22 out of 52, which I can reduce down to 11 over 26, which is approximately 0.423. All right, number 5, still dealing with that deck of cards. I want to know that it is a probability of more than 3 or a red heart, meaning again it's going to be a red card, meaning again it's going to be a heart or a diamond. This is a or statement now, so I want the probability of greater than 3 or it being red. So that is the probability that it is greater than 3 plus the probability of it being red. And then I have to subtract off the probability of it being greater than 3 and red. So the probability of it being greater than 3, it is all of these guys right here. So it's all but 8 of them, which means I have 44 out of 52. The probability of it being red, well, that's half of them, so that is 26 out of 52. And then the probability of it being greater than 3 and red, well, I can take that from right up here. That is 22 out of 52, which if I go ahead and I simplify that, that gives me 48 of the 52 cards, which is 12 out of 13, approximately 0.923. All right, now do these two have the exact same probability? We'll take a look. You have 11 out of 26. You have a 12 out of 13. Those numbers aren't the same there. So we can go ahead, we can say no. And the reason for that is that in number 4, we want the intersection. What they have in common. While in number 5, we want, that's a 5, we want the union. All right, that is combining all. Combining, forgot the N on there. All without repeating. All right, so let's take a look at number 6. Number 6 says out of 200 students in the class, 113 are either student varsity athletes or on the honor roll. It says there are 74 seniors who are varsity athletes, and it says there are 51 seniors who are on the honor roll. What is the probability that a randomly selected senior is both a varsity athlete and on the honor roll? So we want to do the and statement. And is equal to A plus B minus or. Well, that means the and statement, we have 74 seniors who are varsity athletes. We have 51 who are on the honor roll. And we have 113 that are either one or the other. So if I simplify that, I get that that is 12. There was a total of 200 of them. So 12 out of 200. We get 3 out of 50, which is 0.06. Now, I'd like you guys to go ahead, take a look at this last problem, pause the video, and we'll come back together in just a moment. All right, so I'm using this Venn diagram here. I see that there's a total of 23 stars. If I want the probability of A, well, I can count that there's 13 stars out of the 23, which will give me 0.565. If I want the probability of B, I can count the stars. That's 15 out of 23, which will give me 0.652. If I want A and B, that is just this center area, that is 5 out of 23, which will give me 0.217. And if I want A or B, well, that is all of them, which is 1.0. So we've got our probability of our and or our or. Delzati is done. I will